Hello, welcome to the 13th video out of 14, so I'm almost there. From the 2019 AP Calculus AB Standard Quiz Model Overview, we're going to be working through question number 13, which is kind of a one-trick pony. You're basically doing the same thing each time, but especially with the plus question, we'll show you some cool calculator tricks as well that might be able to help you save yourself some time when you're doing some future problems. To start with, let's start with what question number 13 asks you to do. Question number 13 asks you to use a graphing calculator to find all points x comma y where the functions intersect. So basically we're solving equations graphically. We're using our graphing calculator to do that. It's one of the 4 skills that you'll be asked to do using a graphing calculator during the course of this course. So to begin with, I just want to kind of overview the technique that we're going to be going through here, which is using your graphing calculator. So once again, I'm going to be pulling in and using the TI-84 plus CE graphing calculator. So in this case, though, I had the old function that we were looking at. So for us to begin attacking this, when you're using a graphing calculator to solve and find points of intersection, in other words, solve the equation, we're going to need to put in each of the 2 equations as a separate equation, just for simplicity. Then we're going to use the calculator's built-in intersection feature to figure out where they actually cross. So typically, I aim for solutions where there's multiple, or there's 2 solutions. It's usually my goal. Sometimes there's only 1. Sometimes there have been 3 in the past, but rarely. So in here, the first thing we want to do is we want to put in both f of x and g of x in here. So I'm going to put in 2x minus x squared. That's just a nice normal parabola, so nothing really fancy there. Then second, I want to put in 2 cosine of x. As a reminder, we should be in radian mode, which in fact we are. And then as far as graphing these things, I want to just go back to the standard zoom. For the moment, our zoom was kind of off because we're trying to fit that whole parabola, or that whole polynomial in from the last problem. So I'm going to go to zoom 6, the standard zoom, and we'll see what happens. So looking over here, it looks to me like we can kind of see where those things intersect. It looks like they both intersect in quadrants 1 and 4, respectively. But I can't see it quite as well as I want to, so I'm going to zoom in a little bit. I'm going to go ahead and change this to -5 to 5 and -5 to 5. Again, this is purely a aesthetic thing. I just want to see the picture a little bit better. There we go. So I can clearly see that there's 2 intersection points, one right there and one right there. So my goal is to find each of those 2 intersection points. So to do that, I'm going to go back to our favorite button. We call it the Whittler button at school. We here will go to second trace, which will give us the calculation options. And we're going to go down to intersection. So we want to find the intersection of these 2 curves and then record both of those ordered pairs. So for the intersection, you have to choose the 2 curves. I'm going to press enter on the blue, enter on the red, and then it wants us to guess. So in this case, it should pick the one that's closest. I'm going to pick that one as my guess, and it gives me my intersection. So it looks to me like we've got the point 1.049. Just let me get that right. 1.049, comma, 0.998. So we have our first intersection point. We also have one other intersection point that appeared when I looked at that graph. So to find the second one, I'll do the same thing. Second trace, go down to intersection, or select 5. 5 would also get you down there. I'm going to again do enter, enter, but this time I want that point to be a little closer. I could also type in a coordinate most of the time. And it tells me our second point is going to be 2.667. And -1.779. Boom, boom, boom. So there are our 2 intersection points for this first one. And actually, let's see. Can I capture the screen? There we go. Look at that. Question is, can I paste this in now? Darn. I was hoping I could paste it in, but oh well. Wait, maybe I can. File. Watch this. Boom. I don't know why I'm even bothering with this, but what the heck, we're here. Boom. So in case that's interesting later, we've got that covered. Okay, moving to the second one. We're following the same basic pattern, just getting different kinds of functions themselves. So different kinds of graphs for us to attack. So once again, I'm going to go back. I'm going to clear my 2 pieces. So looking in here, I've got 1/3 x plus 1. Now there's a bunch of different ways. You could just type in 1 divide 3 x and then plus 1. But there's this cool feature inside here. I'm going to go to math and then fraction. And it gives us that n over d option. That actually lets us input this as a fraction, which is just kind of a neat thing to be able to do. So we have 1/3 x plus 1. Our second graph is going to be the square root of, it looks like 5x minus x squared. And now we want to find the intersection. Once again though, I had already modified the window, so I'm going to zoom 6 it to make sure I get everything. We can very clearly see our two intersections. And it looks like we got a semicircle and a line, which makes sense. I'm going to go find those intersections really fast. So second calculate, as I said before, we could scroll down or we can just type 5. We'll go enter, enter, enter. Our first intersection is 0.246. Comma 1.082. Our second intersection, I know I saw two of them in there. Our second intersection, we'll again go second trace, go to option 5, we'll enter, enter, and then we'll go over and we'll choose the second intersection point. 3.654 was our x-coordinate, and 2.218 was our second. So there are our intersection points. Nice addition here was in using that fraction thing. It allows us to simplify kind of our work as we go through. Okay, for part C. Part C, basically the same exact thing here. Can you tell I'm getting bored by this question? Yes. But, unfortunately, this one has a lot of complicated stuff. It's a little bit crunchier than some of the other problems that we've looked at. So let's put it in there. Humor me. And again, you can always fast forward these videos if you don't want to go through a problem that you've already fully mastered. But in this case, we are going to need it for the plus question, so I want to do that as well. So there's 2 to the negative x plus sine of x squared. And you'll learn pretty quickly in this course that I tend to choose some interesting functions to work with. We got 3 plus the natural log of 1 minus x. There's our stuff. We'll zoom 6 it. Geez, that's complicated, but we can still see there are two intersection points. Rather than beating around the bush, I'm going to find my intersection. Boom, boom, boom. So it actually found us the right intersection first, 0.834. 834. Our y-coordinate was 1.202. And then our first intersection point here for these two functions that you're probably fast forwarding through, which is fine. And let's go. Yep, that didn't work. I was trying to speed something up. Let's go trace. Oh, that's probably why. Oh, that's interesting. So trace, second calc, 5, enter, enter, enter. Go to. Why is it fighting me on that second intersection point? Huh, it liked me the third time. Negative 2.381. 318, excuse me. And 4.199. So there are our two intersection points. Notice that all three of these examples so far have featured exactly two intersection points, which is always my goal on these questions anyway. Might be 1, might be 3, but goal is 2. Okay, now, the interesting part here. This is where you really make your money on this question. On the plus question, it asks you to use f and g from before, but it wants you to find the intersections of two transformed versions of the functions, f of x over 9 and g of 3 minus x. And in order to do this, I don't want us to have to plug back in. Because for instance, look at f of x. F of x was this 2 to the negative x thing, was it plus sine of x squared? This is just going to be, it's just a messy thing to have to put in. And to have to plug in x over 9 or 3 minus x2 is just a lot of parentheses, a lot of room for error. So instead, what I'm going to show you is that how your graphing calculator actually allows you to do transformations almost instantly. So in here, if we go back to y1, we have 2 to the negative x plus sine of x squared. What I'm going to do first is I'm going to deselect that function. I'm going to do the same thing with y2. I don't want to actually graph f and g because we're trying to find the intersection of these transformed versions, f of x over 9 and g of 3 minus x. In order to do this, what I'm going to do is I'm going to use the fact that our calculator is storing these functions as y1 and y2 respectively. So specifically, if I go into either vars, right down here, I can go into vars or variables, y variables, functions, and I could select, say, y1 and work with it. So in this case, if I want to deal with f of x over 9, I could do y1 of parentheses x divided by 9. And then that will graph f of x over 9, which is what we're going to be having to find an intersection with. The second option is to instead go alpha trace. And when you do, it actually brings up a quick hand menu for the y variables, or whatever variable for the function method you're using. I'm going to choose now for our second one, y2, and then put in parentheses 3 minus x. And what this does is this will now graph f of x over 9, which we're calling y3 now, and g of 3 minus x, which we're now calling y4. I'm going to go to Zoom 6 graph it. So, looks like there's one intersection point. I'm going to zoom out just a little bit, or I'm going to modify the window a little just to make sure that there's not a second one here. You never know. Sometimes you get wrong. Nope, look at that. That one you can barely even see that there's an intersection. So I'm going to go back to Zoom 6. So I feel confident that there's one right there, but just to make sure, let's go ahead and try it. Could be that there's no intersection. That would be a disappointing end to this question, wouldn't it? So we're going to go over. We're going to enter, enter, enter. Oh, and it looks there is in fact one intersection. 2.213. 2.123, excuse me. And second, 0.905. So there's a single intersection for these two equations. But again, we didn't have to do anything fancy. What we instead did was we did y1 of x divided by 9 and y2 of 3 minus x. So using those shortcuts will speed up your process. It'll make you more accurate. It won't require you to do any sort of fancy parenthesis work, and you'll be able to get through the problem quickly. So again, that was a little bit of an exercise in tedium, but hopefully that gave you a few insights and a few nice little tricks that you can apply when finding the intersection between two curves and solving an algebraic equation graphically.